right, supposed to be Mateusz, but probably his supervisor, Christoph, is talking about the tropospheric delay modeling in SLR solutions based on numerical weather models and the estimation of tropospheric bias corrections. Just a moment. This one.
So, thank you, Toshi, for the introduction. I'm going to continue the topic of the tropospheric delay modeling for SLR solutions. And I'm giving this talk on behalf of the first author, so Mateusz, who couldn't come here. Okay, so what kind of errors do we have in SLR observations from the geometrical point of view? We may have range biases. Range biases are constant and they are independent from the elevation angles. We may have time biases. Time biases show up as along track errors in principle. So we have bias in the direction of the satellite motion. We may have a tropospheric bias. Actually, a tropospheric bias is also an elevation-dependent bias. It's smallest in the zenith direction, and it increases for the lower elevation angles. And typically, we also may have the sum of different errors included in data. I would like to show the example of the Grad station. In 2020, a barometric bias was discovered in the Grad station, and afterwards all data were reprocessed and released for the second time to the ILRS database. And here we have the elevation-dependent residuals based on original data as they were originally sent to the ILRS data centers. And here we have the analysis after correcting these data. These are data to Sentinel satellites without estimating any additional parameters. Now, if we estimate only a range bias, this is what happens with original data and reprocessed data with corrected bias in the barometer. So the mean observation is at the level of 0 millimeters, but we still have this slope, so the elevation dependency. And now if we, instead of estimating a range bias, we estimate a tropospheric bias, for the original data and for the reprocessed corrected data, we obtained exactly the same pictures. So we can remove the barometric biases included in data by simply estimating a tropospheric bias. And we see that there is no slope anymore in both cases, and also the mean residual is the residuals are concentrated around the 0 value. What about other parameters? Because from SLR we want to recover not only the quality of the orbit and validate the quality of LEO orbits, we want to estimate also some parameters, especially the station coordinates, and especially station heights are correlated with zenith delays and biases in zenith total delays, so in the troposphere modeling, and also with range biases. To decorrelate station heights, troposphere delays, and range biases, we need to have observations at low and high elevation angles. Otherwise, we end up with very strong correlations between these three parameters. But how the tropospheric biases can affect the estimated station heights? we run a simulation of a tropospheric bias, and we introduce an artificial bias of 5 hectopascals to all SLR observations to LAGEOS. 5 hectopascals corresponds to about 11 millimeters in the zenith direction, and then this bias increases for the lower elevation angles. We processed 10 years of LAGEOS data, and we generated 4 different solutions. The first solution with the estimation only station coordinates, then with the estimation of a range bias and station coordinates, then with the estimation of tropospheric bias and station coordinates, and then with the estimating 3 parameters, 3 types of parameters at the same time. And here we have the results for one station for Graz. If we introduce a bias of 5 hectopascals and we estimate just station coordinates, we will have offset in the up component at the level of plus 15 millimeters. If we estimate a range bias, so we try to use range biases to capture the effect of the tropospheric biases, the offset in the up component becomes negative, and it's minus 16 millimeters for the Graz station. When we estimate tropospheric parameters, we have only a small bias at the level of 1 to 2 millimeters. Actually, the estimated tropospheric biases can recover about 90% of the introduced pressure bias, this artificial bias, which we introduce into our solution. And if we do not estimate a tropospheric bias, we end up with large range biases. If we try to use range biases to absorb the tropospheric biases of about minus 40 millimeters. And if we estimate all parameters altogether, the solution becomes a little bit noisy for the range biases. And now let's have a look at all stations. We have slightly different solutions for different stations because some of the stations provide more observations at low elevation angles. Some stations stop tracking at 20 degrees, 25 or even 30 degrees. So for all stations, if we just estimate station coordinates, the mean bias is at the level of 17 millimeters. Please remember that we introduced this artificial bias of 11 millimeters in zenith. If we estimate the tropospheric bias, the bias for the up component is reduced to 1.5 millimeter. It's negative, and the solutions become a little bit more noisier for the situation when we estimate at the same time tropospheric biases and range biases. If we just estimate the range biases, the up component of station coordinates becomes much more noisy, and we have the negative offset of minus 24 millimeters. And of course, these offsets have an impact on the scale of the reference frame. This is the situation when we do not estimate any parameters and additional parameters to account for the tropospheric bias. And here we have a situation when we try to estimate range biases. And we have 0 values, around 0, when the tropospheric biases are estimated. Now let's have a look at the solutions without introducing any artificial biases. So we have a standard solution, so without estimating range biases and tropospheric biases, we have a solution with the estimation of tropospheric biases, with the estimation of range biases, and with the estimation of both parameters. And we see the station coordinate reparability for the up component. So solution with the estimation of range biases, significantly deteriorates these, for more than 80% of analyzed stations. So we observe the increase in the RMS of the station coordinate repeatability for the orange solution. And solution with the estimation of the troposphere corrections improves 50% of analyzed stations, whereas for 90% we observe no significant differences. For some stations like Yaragadi we have an improvement, the same for Matera. For some stations we have a slight degradation of the solutions. The estimation of tropospheric biases also has an impact on the geocenter coordinates. By considering tropospheric biases, we can change the Y and Z components by about 1 millimeter, and we observe also some seasonal signals. One has to keep in mind that this is the basic product from SLR, and the ITRF relies on the SLR-based geocenter coordinates, SLR-based origin. So we want to avoid any biases in the geocenter estimates. What else is missing in terms of the troposphere modeling in SLR right now? Other techniques of space geodesy already take into account the horizontal gradients of the tropospheric delay. Why gradients are important? Because the atmosphere is thicker around the equatorial area and it's thinner over the poles. So we have the asymmetry, especially for the north component of the horizontal gradients. So for the northern hemisphere, we expect negative gradients. For the southern hemisphere, typically we have positive gradients. For microwave techniques, which are much more sensitive to the wet delays, we can observe much more structures, a lot of structures for the north and east components. For the SLR, we have to take into account mostly the hydrostatic part of the tropospheric delay. And it was already shown today that we have different products that can be used to account for the horizontal gradients, but not only for the gradients, but also for the mapping functions and for the zenith delays. So there is the Potsdam mapping function generated by GFZ, and also Vienna mapping function for optical frequencies generated by Technical University in Vienna. And those products differ in terms of the handling of the horizontal gradient separation between the wet delays and hydrostatic delays and so on, but in principle they give very similar results with each other. We also try to simplify those models for the horizontal gradients. So we put it a simple function of the offset drift, the annual term and semi-annual term for the north gradients, east gradients. Here we have the example of the Yaragadi with positive gradients because Yaragadi is in the southern hemisphere, Simosato is in the northern hemisphere, so the mean north gradient is negative in this case. The same for Hersmonsu and Arequipa. So even if we use a simple function, it's better than not accounting for the horizontal gradients in SLR solutions at all. And why the horizontal gradients are important? If we consider the horizontal gradients, we have in our estimates the offset for the x-pole and y-pole coordinates of about 20 micro arcseconds. And if we compare the estimates, without the gradients and with the gradients with respect to the CO4 series that is based on, in principle, 3 techniques of space geodesy, so VLBI, GNSS, and SLR. We see an improvement and a better agreement between SLR solutions and the CO4 solutions. So in principle, SLR becomes more consistent with our techniques of space geodesy because our techniques of space geodesy already take into account the horizontal gradients of the tropospheric delay in the computations. Those barometer biases were already shown by Van. So using Vienna mapping function, we can compare the data collected by the barometers at the stations with the Vienna mapping function models. And for some stations like Simosato, we may find some drifts. For some stations like Wetzel, we may find some jumps in the data, the same for San Fernando. To sum up, some SLR stations are affected by barometer biases, which can be mitigated by estimating tropospheric delay corrections. Barometer biases cannot be mitigated by estimating range biases due to their elevation-dependent nature. Range biases make the situation even worse because we end up with wrong station coordinates, especially the up component. Barometer biases affect the geocenter coordinates and the scale. Horizontal gradients in SLR solutions should be based on numerical weather models. So we have currently Vienna mapping function, Potsdam mapping function, or we can even use a simple parametric model. We can distribute the Fortran code and the parameters for this model. The estimation of gradients should be avoided in SLR due to the low number of data. The gradients should be considered at least for late geos and lower satellites. For GNSS, there are not too many observations at low elevation angles. Gradients affect the estimated Earth rotation parameters, especially the pole coordinates. In situ meteorological data are good for zenith delays because they collect information from the exact point where the station is located. However, mapping functions and gradients require meteorological information on the surroundings of the station, which is better included in the numerical weather models. Okay, thank you for your attention.
Thank you very much, Krzysztof. Again, one short, quick comment will be allowed.
Christos, so what is your recommendation? What would you have us do then?
Yeah, one thing is to consider the horizontal gradients. The effect is systematic, I would say, for the pole coordinates. So to become more consistent with other techniques of space geodesy, the gradients should be considered. And one could also test the tropospheric biases, the estimation of the tropospheric biases, because it seems that the solution becomes more stable than the solution with the estimation range biases. So it seems we cannot be sure that these parameters absorb only the barometer biases. It can be any kind of the elevation-dependent bias that is absorbed by the estimation of these parameters, because we have only the partial derivatives in our first design metrics. So we cannot distinguish between different types of biases, but it seems that we have more elevation-dependent biases than constant biases in SLR data.
Thank you.
Okay, thank you.